Alright, so in this video, I'm going to be explaining another important paper with the title Strategies for Pre-Training Graph Neural Networks. This iClear paper in 2020. Many applications of machine learning require a model to make accurate predictions and test examples that are distributionally different from training ones, while task-specific labels are scarce during training. An effective approach to this challenge is to pre-train a model on related tasks where data is abundant. And then fine-tune it on a downstream task of interest. While pre-training has been effective in many language and vision domains, it remains an open question how to effectively use pre-training on graph datasets. In this paper, we develop a new strategy and self-supervised methods for pre-training graph neural networks. The key to the success of our strategy is to pre-train an expressive GNN at the level of individual nodes, as well as entire graphs, so that GNN can learn useful local and global representations simultaneously. So we systematically study pre-training on multiple graph classification datasets. We find that naive strategies which pre-train GNNs at the level of either entire graphs or individual nodes give limited improvement and can even lead to negative transfer on many downstream tasks. Transfer learning refers to the setting where a model initially trained on some task is purposed on different but related tasks. And pre-training has the potential to provide an attractive solution to the following two fundamental challenges with learning and graph datasets. First, task-specific label data can be extremely scarce. Second, graph data from real-world applications often contain out-of-distribution samples. So what are the strategies for the pre-training of graph neural networks? So we first describe our node-level pre-training approach and then graph-level pre-training approach. Finally, we describe the full pre-training strategy. So this figure, you see that when only node-level pre-training is used, nodes of different shapes can be well separated. However, node embeddings are not composable, and thus result in graph embeddings that are created by pooling node-level embeddings are not separable. Now here you see that with graph-level pre-training only, graph embeddings are well separated. However, the embeddings of individual nodes do not necessarily capture their domain-specific semantics. And finally, this case, that we have high-quality node embeddings are such that nodes of different types are well separated, while at the same time, the embedding space is also composable. So we have either pre-training at the node level or graph level, and you can see it at attribute prediction or structure prediction. So for node level pre-training, our approach is to use easily accessible unlabeled data. So we propose two self-supervised methods: context prediction, and the other method is attribute masking. You have this attribute, for example, X could be carbon, nitrogen, oxygen, and so it can be, your node can be anything. You are attribute masking. Or you have this method, we have context prediction. You want to predict. So center node, you have the context nodes, anchor node, you have the counter node, and then you get the k-hop neighborhood. I will explain it later. So molecules are very interesting for us. Like if you look at QM9 dataset, you have each atom could be carbon with valence of 4, hydrogen with valence of 1, oxygen valence of 2, nitrogen is 3, fluoride is, I think, 1. Yes, definitely 1 is same as hydrogen. And that's it. We have 5 node types in QM9 datasets. So for every node, we define V's neighborhood and context graph as follows. With K neighborhood of V contain all nodes and edges that are at most K hops away from the V in the graph. And they learn via negative sampling. We use negative sampling to jointly learn the main GNN and the context GNN. But what is the other method, which is attribute masking? It works like this. We mask negative node and edge attributes, and then we let GNN predict those nodes. It's a very old idea based on neighboring structure. Also in, so in molecule property prediction, the raw node features and edge features are both two-dimensional categorical vectors. We also introduced unique categories to indicate masked node or edges, as well as self-loop edges. By the way, this QM9 dataset is undirected. It means for any 2 nodes, there is one direction from source, from this node to a node to the other, and the other direction. So make sure that if you want to calculate valence or anything, you don't calculate anything double thing. You count the bond order all in once. So they did molecule property prediction here. At the case level, it looks like this. The representation looks like this. Here they embed it because it's just a number in a vocabulary, so we embed it. It becomes a vector. Just like you embed words of a corpus, so you embed it into, so you learn the embeddings. It's just a linear mapping from 1 to n. And then embedding for this, and then, so the graph level representation is mean pooling of them. For example, for protein function prediction, this is very interesting, that the GNN architecture used for protein function prediction is similar to the one used for molecule property prediction, except for a few differences. First, the raw input node features are uniform. And second, the raw input edge features are binary vectors, which we denote as C sub E. So we concatenate the 2 vectors. Since the downstream task is ego network classification, we use the embedding of center node together with the embedding of entire ego network. Of course, you can use graph sage, graph attention, graph convolution, or any other thing for your core GNN architecture.